So I think the stream is going. Not 100% sure. Hey, Derek. Me too. Hello. Okay. So we are streaming then? Okay. That doesn't look like they can hear you though. So hold on. That's Ubuntu 16.4, man. That's what we got. Yeah, it doesn't work on 16. Yeah. There's some dependencies on 16 that don't work, and I am one of the 3 people that likes Unity, so I haven't moved past 16 yet. I know. Why? Properties for desktop audio, default USB. Oh, that's what we're doing. Okay. Say something, Derek?
Hey, how's it going?
Yep, okay. I see your VUs moving up and down. So, next thing, I need to add a thing to this video capture. No, window capture. I think I want window capture. Create new. Yeah. I'm going to click OK. No, what are you? Zoom meeting. Zoom meeting, I think that's the one. Nope. Failed. Why failed? Is Zoom not letting me grab from OBS? No, it looks like nothing is grabbing from OBS. What the hell? Desktop. Screen capture. Window capture. Nope. Minus. Yes. All right. Is the chat room laughing at us yet?
Oh, yeah.
Oh, good.
But
yeah,
we've only got 9 people that were wasting their time, right?
That's a big stream for me.
Oh, well, I shouldn't have tweeted.
No,
Setting expectations.
That's right. All right, I'm going to put you down there so people can see you at least.
Oh, that's fun.
And then I'm still working on getting... I'm trying to figure out how to capture that in Zoom. Or in OBS. So, here, let's go ahead and share with everybody. So, in OBS here, there's me down in the corner. And I should be able to do a window capture. So video capture is my camera. Screen capture is the entire desktop.
Yeah. Okay.
So I think
I can see myself now on the stream.
Yeah. So window capture, zoom, make source visible, click OK. And then I need to be able to... see, it's the Zoom meeting that I'm trying to do, and then like OBS freaks out. This is the console of OBS. It's like GL get error returned O2 device copy texture GL failed. So, all right, you know what? Oh no, don't close the terminal. We're just going to do this.
We were talking about IQ sampling, not
video streaming.
OpenGL settings.
Yeah, this isn't even OpenGL. This is OBS.
I was actually messing around with OBS just before this call. I picked my yet another project to start.
Speaker view. Okay. All right. That's how we're going to have to do this. Cancel. Zoom. Yeah, that's not working. Remove that. There we go. All right. So we do that. Maybe we do that. And then I've got that. And if I do that, okay. I'm not going to be winning any YouTube awards, but this will get the job done.
You promised me absolutely rock bottom low standards on this stream.
And I promise to deliver.
Awesome.
I will deliver absolute rock bottom standards. All right, I'm not paying attention. As is evidenced by the fact that I'm eating a cracker on a live stream. What kind of an idiot am I?
Hey, I'm in stereo.
Am I only coming out one channel?
Yeah, you're only on the right channel.
What the hell? Kids, this is why you test things out before you go live. Check one, check one, check one. That's my mic. Wait. The VU comes up on the other side, too. I don't know how to do this. All right, well, can I set that? Advanced audio properties. Down mix to mono. Yes. Down mix to mono. There we go.
So
now I'm stereo.
Now, 11 people that we've got watching.
Sweet.
Of course, one's me, so we can make it nice around 10.
So today on How Do I SDR, we're going to learn how to set up OBS.
Yes. So I'd like to first dive into color correction on OBS.
I got nothing.
Well, I might have something by the end of the year.
Okay, cool. The end of the year sounds like so far away, and then you realize, like, no, that's next week.
Hey. We have a week and a half left.
That's right. You're good to go, man.
No pushing me here.
All right, so let's go read the chat room, see what we've missed. Curious about how to take an IQ signal and combine it. Yes, combine is a very ambiguous term that I've been trying to figure out as well, but I think I have some answers on that. Stream is up. I can see Mark in the bottom right. Yep, okay. I can hear Derek now. Okay, cool. I'm around somewhere. Yeah, we're working on it. Oh, hi. Hey, Kenneth. And I think I saw Nick up there. Yep, Exploding Lemur is up there as well. So we have our two, the Wrenchy people. What are they? Moderators. In the channel. Good. And by moderator, we, of course, do mean peanut gallery.
Yes.
Yes. You should put your phone number on there. What? Did I do that? Oh, no.
No.
Oh, yeah, Kenneth.
I had a great call with him last night.
Yeah, me too.
Yeah, good fun.
I only hear Mark in the right channel, though. Yeah. Sorry about that. Is that an IQ? Yes, I'm only in phase. You don't get to hear my quadrature signal. Okay, wait a minute. Negative feedback. Oh man, my entire life is about negative feedback. Success. Peanut Gallery represent. That's right. Okay. Hi.
Hi.
I'm Smitty Halibut, and with me today, above me, is Derek Kozel from GNU Radio. Say hi, Derek.
Hi, folks.
So we did a video, an audio. We did a podcast with the Ham Radio Workbench with George, I'm not going to butcher his last name, KJ6VU, and we talked a little bit about SDR. And in that presentation, we talked about what is SDR and how is it different and how is it similar to hardware-defined radio, HDR. We talked about, like the platonic form of the SDR is you have an antenna going straight into an ADC, and then you take the ether, turn it into numbers, and process it in numbers. But most real SDRs actually have some amount of hardware in before that for tuning, filtering, various other things, amplification and whatnot. And so you end up with some subset of a full HDR kind of radio. But the thing that makes an SDR is that at some point you take those signals and turn them into numbers and do math on those numbers to process it in some way before using the end result. So a lot of the times that will be used for digital signals like FT8 and whatnot. But also sometimes you might use it to process audio signals like single sideband and AM, FM, whatever, to be able to do kind of the filtering. And so there is no one definition of what is an SDR. SDR is just we take the electrical signals, we turn them into numbers, and we do math on those numbers at some point. And there are a lot of different ways on doing that. What we did not get into in that podcast is talking about what do those numbers look like. How do we actually perform that math? We kind of waved our hands at it, and we kept it a very high level block diagram, connected the signal from here to there kind of things. And I opened up GNU Radio Companion actually once before that podcast and several times since that podcast, and I was trying to understand what I was seeing. And unfortunately, so chat room, are you able to read what I've got here, or is my screen resolution too high to make this, because I'm only streaming at 1080p, but my monitor is actually 1440p. So we may have to take a break here and actually do some more OBS magic to get this to work out properly. But
what version of GNU Radio are you on? Can you zoom in on the canvas?
3710.
3710.
I don't.
If you hit Control and scroll in and out on the canvas, does it zoom in?
Nada. Bummer.
Okay, well, look forward to that in your near future.
Well, I got to get up to something more modern than Ubuntu 16.04. I am one of the 3 people that liked Unity and was not ready to upgrade to GNOME 3 with 18.04.
I've got great news for you. Apt install Unity Ubuntu Desktop.
I tried that on 18 and it sucked. The support for it was horrible.
Okay, that I can believe.
Yeah, it's there, but yeah, the support for it was rubbish.
Chat says tiny but readable. Readable if they can squint.
Okay. This is the joy of being a live stream. Let's fix this. Okay. We're not going to bother doing this whole live stream if nope, not sound. Just kidding. If people can't actually read what we're doing. So I'm going to take that and turn that into a 1080p monitor. There it is. Apply.
So for the peanut gallery / audience, when I'm staring in this direction, that's because I'm actually watching the live stream. When I'm staring straight forward, it's because I'm looking at my own flow graph or screen. I've got the 2 monitors set up. Looks like you have 3.5, which is great.
Yeah, my capture has lost its mind. Desktop camera inserts a screen capture.
OBS uses, I think, XRender for grabbing stuff. So yeah, when your geometry changes, it
doesn't like it. All right, I just needed to reset. It looks like it's better now. Maybe. Okay.
Ooh, lots of me.
Hello. Okay, I'm gonna make you a little bit smaller.
10 seconds behind. Okay, so this is gonna be great. I'll try not to look at the live stream very much.
Okay. So now we got some scrolling we need to do, but we can make that work. All right. So the way I'm viewing OBS looks like we've got me in the lower right corner, you in the upper right corner, and then GNU Radio over on the left-hand side.
Looks good.
We got a pass GNU Radio on the left-hand side. Oh, that's something else. Never mind. Okay. So, okay, chat room. Is that more readable now? Because at least I'm at a 1-to-1 resolution. I'm not trying to rescale anything. 2021 is the year of the Linux desktop, just like it's been for the last 20 years. Now, to be fair, I've been using Linux as my desktop since the 90s. There was a brief period where I was using Windows 7 for a while. Windows 7 was actually quite a nice operating system, but yeah, I just like Linux. It's just my thing. All right, more readable. Very good. I'm trying to get my tea. Okay. So, YouTube is not receiving enough video to maintain smooth streaming. Oh, for Pete's sake. Shun the non-believer. I know. Wait, Linux has a GUI. All right, I got to stop reading the chat room. I've never had a chat room this active, so this is kind of rad. Okay.
17.
I think I've peaked out at like 7, maybe. Anyway, so, all right. Derek assigned me homework that I watched. 2 great videos from Alan Wolke. I don't know how to pronounce his last name. Is it Wolke? N2AEW?
W2AEW.
Yeah, that guy.
Yep.
Go ahead.
He's great. I mean,
yep.
This was videos 170 and 171. He's now up to 300, 400, and they're just fantastic.
Is he the guy that works for Tektronix?
He is indeed.
Okay.
Yes.
So obviously,
he's got all the nice toys.
All of his gear is tech gear, of course. But he does a really good job of explaining I and Q, in phase and quadrature, sometimes just referred to as quadrature signals. I'm not going to do as good a job as he did of explaining it, but I do want to very quickly summarize, because what the answer to one of the questions I'm going to ask is it's quadrature. And so without explaining what quadrature is, that's going to be a little bit hard. So again, I hate doing math, but we can at least kind of understand at a high level what's going on. Let's say you've got a sine wave and a cosine wave. They're off by 90 degrees, right? A quarter of a cycle. The cosine starts at the very top and goes down. The sine wave starts at 0 and goes up before going back down again, right? And you can generate any waveform, any amplitude, and any phase by just summing a cosine and a sine wave of different amplitudes. Especially if you include, you need to include negative amplitudes as well. But if you have an amplitude of a sine wave and an amplitude of a cosine wave between 1 and -1, and then you add those 2 signals together, you can represent any amplitude of that sine wave and any phase of that sine wave, right? So if we're talking about only a single, tone, a single frequency tone, a pure tone, you can represent any amplitude and any phase of that tone by talking about the amplitude of its sine and the amplitude of its cosine, all right? That's the simple case. If you take that and generalize it to any frequency, not just one tone, but a given signal can have multiple different tones in it, or can have multiple different frequencies represented, and you sum all of that up, you still can represent any signal by the sum of the sine and the cosine of the frequency, of the tones that make up that signal. And that is basically what I and Q is. So you've got this, the I, which is the in phase, which I think is cosine. It's somewhat arbitrary as to which one's which, but I think the in phase is the cosine. And then the quadrature is the sine. And so if you view the I and the Q as the amplitudes of each of these signals, then you can represent any ultimate signal. What I don't grasp yet is, how do you do that in a time series signal? And we're not starting at the beginning on this one. I don't want to have to try and explain everything from the beginning, but this is ultimately the thing that I don't get. I understand what a time series signal is if you're just looking at the amplitude of the signal, right? That you look at a waveform on a screen. Like if you're recording audio through a microphone into a sound program, what you see is the time series signal, and it's already the sum of all of those things, right? And that is literally just what's the amplitude of the incoming signal at this period of time, what's the amplitude at the next period of time, what's the amplitude at the next period of time, so on and so forth, right? I understand that. I also understand how I can take a block of that, feed it through an algorithm called an FFT, or a discrete Fourier transform, which is usually implemented using the fast Fourier transform. Anyway, you do a Fourier analysis on that, and that block of signal becomes a series of amplitude values for each of the frequencies that are represented in that block. And that is not a time series anymore. That is a frequency series, right? And so I get that. The part that I'm having a hard time wrapping my brain around is, how do I represent that sine wave and that cosine wave of each frequency in a time series signal? Are you able to answer that question for me?
So your question is, what does a quadrature sample look like in the time domain as a single element? It's like if you tried to look at this on an oscilloscope, what would it look like?
If two oscilloscopes, or a two-trace oscilloscope, yeah, because I've got the I and the Q. Yes.
So, all right, here's where I should throw in all the great disclaimers, especially since you used the word GNU Radio and Derek Kozel of GNU Radio. Yes, I'm involved in GNU Radio, but please do not judge the entire GNU Radio project and its members based on my knowledge. I prefer.
So disclaimed.
I have enjoyed breadth over depth, and it was really fun starting to, when you started asking these questions, because I rapidly started to running into the point where I'm like, I can use quadrature sampling and I understand complex numbers, but where do they become necessary? Like, why are we using them? And I started drawing a lot of blanks there. So, okay. If you had, you're most familiar with audio signals.
I am.
And so there we are dealing with a complicated signal, which ranges from basically DC to 20 odd kilohertz. And so it's all positive frequencies, and yeah, you end up sampling it and you get just a real valued time series data. And that's sufficient to completely represent all of the audio information. So everyone who goes crazy and starts, sampling at 92,000 hertz, is listening to stuff that only a dog can hear.
I'm an audiophile, so I have opinions on all of this stuff, but continue. That's a subject for another podcast.
Yeah. A few things that I started kind of plugging together were like, okay, but in non-ideal SDRs and stuff like that, okay, I can start seeing some really compelling cases for quadrature sampling. But the basics of what you were looking for is, what does this signal look like if you're just viewing it in the time domain? And the simplest thing to do is actually just do this in GNU Radio, where we can start playing with these concepts and twisting knobs and stuff like that.
Which is what I started doing this morning before the call started. Why I've got a signal source here and the RTL, and then a couple of different syncs for viewing it. So let's drive me through it, and let's go view these.
So let's make a new flow graph, because I don't like the one you've got. Rule number 1, never look at anything on the air when you're trying to understand something.
I could just remove the RTL if you need, but anyway.
No, so what I actually want to do is I want to create this flow graph using float signal sources, and then compose a complex signal out of that.
Okay.
So that we can start, from things that hopefully are really more intuitive, and then build up to a more complicated setup.
Perfect.
So if you can drop in two signal sources. Oh, and I'm going to be 10 seconds behind, so I can't see what you're doing on your screen. So you're going to have to let me know when you're.
You're right. Can I share my screen with you?
If it doesn't break, you definitely can. I don't know whether or not that'll break OBS.
Let's find out.
Let's find out, because Hey, I see it.
All right.
We'll find out
Unfortunately,
in 10 seconds if stream can still see it.
yeah. Oh, sweet. And I can still view you in big. Okay.
Awesome.
So it does not look like it broke OBS because I've got the live preview of OBS on my top monitor. Okay.
Cool.
So you're still big, I'm still big, and
Awesome.
you can see my my desktop in real time. Okay. Cool.
Yeah. So pop open this signal source, the top one, and I
Get float.
7, 8, 9, 10, 11.
What's up?
12. Oh, I think you're sharing. I think you're sharing just the window, not your entire monitor.
Oh. Yes. Okay. Hold on. I can do that as well. So, stop share. Share screen. You're right. You're right. It was just a window.
How's our? So in chat, yeah, Linux has a GUI. Next year you will enjoy Linux more. It's true. Windows 7, that's a brave choice, but I run Windows 10 on occasion.
My sim racing rig is Win 10.
Quadrature is maths explained with more maths.
Pretty much.
We're going to try and avoid some of that, but yeah, some of that's inevitable. And yeah, things did not break, which is good. Is there anything else? Yes, this is K0ZEL, although I more commonly operate these days as MW0LNA. So cool. That
because whales.
Yes. And because cooler call sign.
Yeah.
Microwave low noise amplifier, I will take that one.
All right, are you able to see it now?
I am able to see it. Cool.
Okay,
so you
good.
Converted it to a float. Great. Yeah, that's fine. Convert the other one to a float as well.
And make wine a sign.
Change it to a sign, yeah.
Yep. Okay.
And hit OK. Great. Now pull in a Qt time sync.
And I will explain what all of this is when we get there. And then do you want to float to complex, or can I convert this?
No, let's keep it 2 channels. So convert that to float and change number of inputs to 2. It is the second green box.
Number of points, number of inputs, 2. Okay.
But you are quite right that you could have done a float to complex there. But let's work from first principles. Oh, sorry, and throw in a throttle block because we are purely in simulation. By default, GNU Radio will run as fast as it possibly can. And because we are purely simulating, we want to slow this down to a rough average of 32,000 samples per second.
So put it in between each of those?
Just in between one of them will be fine.
Okay.
You need a throttle block in between somewhere in each connected set of blocks. So if you copied and pasted this whole thing, you would need a second throttle.
Got it. Okay.
Yeah. So you should be able to run this now.
All right. And
it'll ask you to save it somewhere and all of that good things.
Ignore my files. I've got a lot of crap on my computer. I've got a GNU Radio directory in here somewhere. Yes, I do. How do I SDR?
Yeah, Tim, it's a good thing we're not in a conference, and if we were, that's why everyone's pre-recording things these days.
Right. Derek's example. There we are.
Cool.
Wait, hey, no, there we go.
So this is basically a 2-input oscilloscope trace. So we have 2 sine waves going from +1 to -1. And if you just click and drag, you can actually zoom in on a bit.
Just kidding.
So if you scroll, I think in this version, it should still... Hey, cool.
Okay.
This is a sine wave and a cosine wave.
Sure enough.
Nothing more complicated than that, which is great. So that's our time domain signal currently.
Yep.
So let's close this and I guess pop quiz. What do you think the frequency content of those signals are at this point?
Pretty boring. Probably one tone. Well, the sum of them is going to be one tone at 1 kilohertz with a phase of 45 degrees.
If you strictly added those two values together, yes, and you would get a peak amplitude of
1.4 or whatever it is.
Yeah, that sounds about right.
Yeah.
Square root of 2?
Yeah, root 2. 1 squared
out?
plus 1 squared. Square root of
Yeah.
1 squared plus 1 squared. So root
Yeah.
2.
Cool. I still remember something from my signals class. This is good.
And
so
if you're wondering what the hell we're talking about, go watch Alan's primers. The links are in the description below. But he describes how the I and the Q sum together and make the phase and the amplitudes and the things and the whatnots.
Or Mark, you can open up the time sync block and add a third channel.
We're going to demonstrate it ourselves. This is rad.
Oh, goodness. This is why I said very much off the cuff. We're going to make this up as we go along and hopefully answer questions. So drop in an add block now. Hopefully also, if anyone's here for the first time doing, using GNU Radio, so hit OK, click on the add block, and just hit the up arrow key for me while that's closed. Ooh.
Fancy.
So you can change the data type.
There you go.
Handy tips and tricks.
I assume this is what we're doing?
Yeah.
Okay.
So run that up.
All right. So, and then that. Look at, oops, hey.
So first fun bit, we put in two sinusoids that are out of phase by 90 degrees. And when we add them, we get one sinusoid with a proportionately larger amplitude. And let's totally skip the math on how we came up with root 2.
Sorry, nerd.
Unless you want to.
Sorry, Nerd Garage. Yeah, we did it in our head. The only reason I was able to do that in my head so quickly is because I literally just watched Alan's videos yesterday. It's vector math. If you've got a unit circle, anyway, never mind.
Anyways, that's why we're not going there.
That's why
this is what I love about teaching people the real basics of SDR using GNU Radio. Is you let the computer do the math for you. Eventually, you need to go and do it yourself if you start writing a lot of DSP, or even probably a little bit of DSP. But you can get started without any math here.
My goal is to understand this at a instinctual level, not be able to derive it myself. I want to understand kind of I want to grasp what's going on without having to know the exact math, right? So you got a sine and a cosine, you add them, the resultant phase is halfway between it, right? I'm not going to show you how to determine that. And if you make one of them negative, which I think is what we're going to do next, it will, shift the phase way all over the place. And so we're going to be able to demonstrate all of that. I just want to understand that that's what happens. I don't need to know why that happens or how that happens.
Frankly, that's basically the level of understanding that I'm at, with a little bit more. But that's because I've been using these for years and I've just kind of picked up eventually more and more of it.
Yeah.
But this is something where I deeply admire people like Marcus Muller and like a lot of the other people who were involved in the project, Mark Lichtman, where they have just this phenomenal understanding of the base theory. And that's something that I've had to learn over time. It's not something I was ever taught. But yeah, cool. Okay. So we have two input sine waves. We add them together. We get another sine wave. The frequency of this sine wave has not changed. It is still a 1 kilohertz sine wave. So the frequency hasn't changed. The amplitude of the resulting wave is larger. And the cool thing is that the power of a signal is the square of the amplitude. And so, hey, cool. And so if we calculated the power of the green sine wave compared to the red and the blue, we would find that the green was double the amplitude.
Oh, yeah.
Double the power.
So
Yeah.
I made our sum a unit 1 by making the 2 sine waves that made it up um, root 2 over 2, I guess.
Hmm.
707. Yeah.
Yeah.
Again,
Cool.
this is what I get for having an engineering background. I remember these numbers. I don't always remember what they're used for, but I remember them from university.
Yep. Yeah.
Okay. So
Cool.
how do we, like, I can see how we can get, like, vary these amplitudes and move the sine wave kind of from here to here. Like, if I take one of these and set it to 0, here, I'm going to set this one back to 1 and set this one to 0, right? So we have our cosine wave, but we don't have any sine wave. What's that going to look like?
So because you didn't have any Q component here, any quadrature signal,
Yep.
the result is a 0 phase shift, 0 amplitude change between the
Yep.
two.
So unsurprisingly, the result is exactly a cosine. And
because you've added a cosine to 0.
exactly. So let's add just a little bit of sine left, or sine back.
So you're playing with different amplitudes, which is interesting. Something that would...
Well, remember, in an IQ signal, all you can play with is the amplitude.
Yes.
Right? If you want to shift the phase of the resultant signal, the only thing you can play with is the amplitude. Right? So what have we done here? I don't know if you guys can see it very well. Let me zoom in a little bit more. But the green is the result. The blue is still our cosine. The green has been shifted a little bit to the right by adding a little bit of the sine.
Do I have... What I wish I had immediately on hand is the formula for... Because what we can see here is that the amplitude, we're not only getting a phase shift, which is what we kind of want here, we're also getting an amplitude shift. And it would be really nice if we could basically fix the amplitude of the green wave to be a perfect one.
Yeah, if we to do that, we gotta we end up scaling our sine and cosines by Pythagorean theorem, and
yeah.
I'm not interested in doing that math. Normalize all of this. Assume that this was scaled such that green is always 1.
Here's where I'm just always wishing that I had... I know I've made this recently, but I guess we can pass by that. Let's start looking at this in the frequency domain.
Okay.
So that's not the window I want. I want yours. Yeah. So drop in a frequency sync, and let's change this to a float.
Does it have a number of inputs, or is it still? Yep, it does.
Yep.
Should I only be looking at the sum?
No. So look at... First, just grab 2, and we'll look at the 2 inputs just to convince ourselves that we're all happy.
Same ones here?
Yeah.
Okay. Yeah, this is getting ugly.
Can you drag the time sync upwards? I think will help most in the layout.
Okay.
The new curved lines do help with this.
Yeah, they do.
Yeah. They are otherwise a bit weird in layout, but they are nice.
Okay. So, chat room, we got 2 signal sources, and basically I'm sending them to both the time sync and the frequency sync. And then I'm also sending them to the addition, where I'm summing the 2 signals together, and the output of that is just going to the time sync for now, although I suspect we'll watch it in the frequency sync in a bit.
Yeah.
Okay.
So if you hit run here, I can't remember what the default is going to be. Yeah, it is. So we jump right a step. So we can see that there's a 1 kilohertz sine wave here. So all the energy is at 1 kilohertz. But there's a property of real valued signals that they are symmetrical across the frequency domain. So you get a negative frequency for these sine waves. And that doesn't matter at all when you're talking just audio. because your inputs are all positive frequencies. But one of the things that I came to kind of realize that it's really useful. First of all, it's really useful to realize that this is just part of how the math works out. And we can actually see that working in physics when you do a classical AM modulator and start broadcasting AM. So if you just have a microphone running straight into a mixer and you set that to 1.8 megahertz or something, get yourself into a ham band and you start just blasting out AM. What does the spectrum actually look like there? And we could set this up, but what you get is you get that main central carrier, and then you get two sidebands, right?
Mm-hmm.
You get the upper and lower sidebands, and they're mirror images of each other.
So I understand that from a mixer perspective, because at one point in college we went through what a mixer does and we did all the math and we proved that the output of the multiplication is the sum and difference of the two input frequencies. And so like I understand that. I couldn't explain why it is that way, but I understood it at one point, the math behind it, and I have accepted it as a given ever since, that that's how a product mixer works. What I still don't understand is we only have fed in, we have fed in a single tone. Why is this showing two tones? And I understand that it's the same tone on either side of 0, but I'm still having a hard time with negative frequencies.
These are both valid answers. It's kind of like if you look at a parabola and you say, where does it hit 0? And it's going to hit in 2 places, or none, or 1, depending on what you do. But there's multiple answers that are valid to that equation. And it's the same thing here. The negative answer is just as mathematically valid as the positive one. And so when you run the Fourier transform on it, you get the positive and negative values out. And so if you close this, GNU Radio helpfully has a drop-down that says, please only show me half of the spectrum.
Yeah.
I know that there's negative frequency spectrum width half.
And bloop. And when you feed a float into a time or into a frequency sink, that's generally what you want to do.
Yeah. And so this is generally what we want to do, because it is taken as a given that that the negative reflection of this exists, and that if you do different math operations on it, you'll start pulling energy from that negative answer and end up with it in the positive realm, like if we mixed this with a higher frequency right now.
Mm-hmm.
And so this is where I start getting a little bit fuzzy off the top of my head. I think if you literally multiply one of those inputs by like a 10 kilohertz signal, I think we'll get, the actual kind of AM type representation that we'd expect, where you'd end up with 2 sides. But this is where I start wondering, okay, do we need to start moving to Quadrature already? So Tim, yeah, we'll jump this into a Constellation sync in a moment and start displaying I and Q with X and Y axes.
The up arrow, you said? Snazzy. Okay.
Which is, incidentally, exactly what Alan does in his video. And I think it's a great illustration.
Add a third input. Okay. So I think that's what I want, right?
Yeah, this is what I'm imagining. I'm wondering what the result's going to be, but that's because, hey, good.
That's exactly what
my
we wanted it to be.
My intuition is correct. I don't operate much with real valued signals. The thing you find in DSP is that you just end up with IQ everywhere. And so I fully admit that I am rusty on my intuition of what happens with real valued signals, but cool, this worked. If we undid that half display, we would see that there are 2 peaks also on the
the other
negative
side.
Because this is still a real valued signal that we're looking at. So it still has a frequency domain reflection here.
Look at that.
Yay.
Woohoo! I'm kind of curious why we have these lobes on the inputs.
Oh, take a look at the left axis here, the y-axis, at the power levels that those lobes are at.
So is that just aliasing from our sample rate?
It is mathematical errors in it's the precision of a float.
Okay.
So that is noise and garbage
Okay.
due to the fact that we don't have perfect numbers.
Okay.
But
we
this
do
is
on
also
on the sum and the difference. That's what I find hilarious.
The power levels are just enough dBs down. They can't see it, probably.
Yeah. All right, so let's explain what we just saw here. Okay, so I put it back to half, so we're only looking at half the spectrum. Okay, so what I did is I grabbed my 1K audio source. I just grabbed one of the two. Yeah, just grabbed one of the two, and I mixed it with a 10K, right? So this 10K is my local oscillator, and I did a multiply. And when you are in hardware and you have a mixer in the RF sense, not a mixer in the audio sense, but a mixer in the RF sense, which is a product mixer. Product meaning multiplication, right? As opposed to the sum meaning addition. So instead of a summing mixer, this is a product mixer. It is multiplying 2 signals together. If you look at what a mixer does, it basically multiplies the 2 signals together. And so mathematically, we have here a mixer. This is what you do in hardware when you have a mixer. So we've taken a 1K and a 10K, and we know that the output of a mixer is the sum of the 2 frequencies and the difference of the 2 frequencies. So in this case, we have a 10K carrier plus 1 kilohertz, so we have 11 kilohertz, and then minus 1 kilohertz, so we have 9 kilohertz. And that is exactly, excuse me, that's exactly what we see here. Our 10K right in the middle, and then we have 11 with a signal here and 9 with a signal here. So that's what we're doing there. That's our AM signal. Although there's no carrier, I never fully understood. Is the carrier of an AM signal just leakage through the mixer, or is that something that's added back later? I never fully understood why mixers leak through the actual the carrier as well. But
so leaking through the leaking the carrier, I think, is a combination of
just imperfect hardware.
Tim's saying DC offset, which maybe on a physical AM modulator, that's what you get. So if you have a 0 hertz component to this, which we can trivially add to this, then you end up with. Can
we do it here, or do I need to?
Offset is the phase.
Phase, yeah.
So you need, I think it's
a constant.
Pretty sure that's the phase. So you need another add block in to put that in line. Actually, there's add const.
Actually, yeah, that would work too.
So you get physical leakage across the mixer, where it's literally just the LO jumping between the pins and through the substrate. And then yes, any DC component will be a 0 hertz signal, where when you multiply it with the local oscillator, you'll end up with some of the local oscillator frequency, because 0 hertz times your local oscillator, or added with your local oscillator, will give you that.
Oh, but that's giving it to me down here.
You've probably added it in the wrong spot.
You're right. I did.
Yep. But this is where I sit and encourage the 15 people who have stuck with us. I'm glad we've run a few people away. If this is not already second nature, and like Mike, if you're still watching, then this is probably second nature. But
Curses.
People who don't, it's a great chance to explore things.
Wrong place again.
Because you start seeing the effect of these different effects in the time and frequency domain, and it's it's a heck of a lot easier than building it out on your bench.
There we go.
Also, I certainly recommend it. Cool.
So there's our courier.
Yeah. So
okay.
We can start doing entertaining things here if you want. We can make our local oscillator quadrature. But leave the input signal as a real one.
So is that what you mean?
Yeah, so that's the only change here. And what we would see in the frequency domain, and maybe we're jumping a few steps here, but what we see in the frequency domain is that the, sorry, getting distracted by chat. What you'd see in the frequency domain is only the positive frequencies. And I guess that's the key takeaway is why do you only get the positive frequency there? So in order to do this now, we'll have to put in a float to complex and a constant source to turn that one into an in-phase signal plus a 0 Q.
Oh, got it. Hence the constant. Okay. Okay. Source. Constant is already set to 0. All right. So let me explain what we've done here. So we've got our sine wave that we're sending into one half of the complex. Okay. You know what we haven't actually done? We haven't actually described what the hell complex is. So mathematically, complex numbers are a real and imaginary component. Hand wave, it gets used a lot. Really what it is a two-dimensional number. Ultimately, that's all that matters. Ignore the I, the square root of -1, the impossible number, right? That's just a mathematician's masturbatory way of justifying that this is a single number. All it is a two-dimensional number, all right? So when you're measuring the complex impedance of your antenna, the two numbers are the resistance and the reactance, right? But there's nothing special about that reactance to make it a complex number. All it is a two-dimensional number, and they just happen to assign one of them as this square root of I, which kind of puts it in a realm where the two numbers will never mix, right? So it's a way of saying resistance and reactive, or in this case, in phase and quadrature, right? A complex number is just a two-dimensional number. It's an array of two numbers. That's all we care about, right? So you can ignore the whole square root of -1 shenanigans that we play to make it work mathematically. Just view it as a two-dimensional number. So what are we doing here with this float to complex? There's no options in there. What are we doing with the float to complex? All it's doing is it's taking... Sorry, what have we talked about with floats? A float, the term float comes from floating point, which is the computer way of representing a non-integer number, a real number. So pi could be represented as a float, 3.14159, blah, 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 blah. Pi could not be represented as an integer, because as an integer it would be 3. And that's not very precise, right? So floating points get you that... it's like scientific notation, right? You have one significant digit to the left of the decimal point, and then the rest of your significant digits to the right of the decimal point, and then how many, like how many places do you move that period, right? So scientific notation is a floating point for humans. Change decimal into binary, and very specifically specify how your bits are laid out between mantissa and exponent. Mantissa? Is that the right term? Mantica? No, it's not lard. Whatever it is. The number...
Mantissa. Yeah.
Mantissa. The number and the exponent, right? That's a floating point number. So floating points are one-dimensional, right? We use floating points in computers just so that we can have precision where we need it, right? So It can represent very, very, very small numbers and very, very, very big numbers. So floating points are that. A floating point is just a single value, though. A complex number is 2 floating points. That's all it is. 2 floating points. It's a 2-dimensional array. Excuse me. It's an array with 2 values in it, with 2 floating point values in it. And in SDR, we're using those complex numbers to represent in phase and quadrature. The amplitude. All right, no, but it's not the amplitude. That's what I'm getting messed up with, because it's a time series of the in phase and the quadrature. You've got 2 sine waves that are being represented in there, but one of them is always a sine wave and one of them is always a cosine wave.
Mm-hmm.
Yeah. Anyway.
So there's, and here is where I start getting a little bit fuzzy, because there's a formula called Euler's equation, which allows you to convert an amplitude and a phase into a sine and a cosine wave, which is super cool.
An amplitude and a phase into a sine and a cosine. Okay, yeah. I agree that those should be convertible.
And they definitely are, and they definitely work that way. But I don't know where that ends up attached to quadrature sampling as a concept. It's definitely where you get rectangular versus polar notation of complex numbers. Because, here's where we start getting into math, but e to the j sine of theta. So an amplitude scaled by times e to the j phase, theta, is convertible into an amplitude of a sine wave and an amplitude of a cosine wave.
It makes sense. We can represent any phase and amplitude of a sine wave by just summing a sine and a cosine with, by representing the of different amplitudes, right? So it's hand wave math, Euler's stuff. It's spelled Euler, by the way, but it's pronounced Euler. I remember that much from college. Math, you can convert back and forth between this amplitude of a sine and a cosine and the ultimate amplitude of the signal and the phase of the signal, the time shift of that signal. It's still 2 numbers, right? Exactly like you described. It's rectangular versus polar coordinates. It requires the same amount of information to represent the same thing. It's just a matter of what format do those numbers take. How do they represent the signal that we're doing? So that makes a lot of sense. Approaching helmet fire? Is that like, too much math? I have no idea what's going on. 50 tabs. Yeah. Yes, Tim, I think you're right. Euler found this after dropping like 50 acid tabs one night.
I can't believe the number of times I've encountered all of these concepts in slightly different ways, in slightly different formats, and each time I take a little bit more away, and I'm still just waiting for that total moment to click, but I realize that moment's never going to come, because you're always looking at this concept with just different bits and pieces, and different expressions of the same ideas are useful in different contexts. So, quadrature sampling, complex numbers, amplitude and phase, these all are just start getting really weird, and different bits are useful in different times. I have something on my screen which is fun, which ends up getting into like, what do complex numbers look like, and what is a quadrature signal actually look like, and where do we get negative signals? So let's try and, I guess, finish up with the flow graph you have, because that is a fun little thought experiment.
Okay. So I've got my 10K signal, and I've got my converted to complex 1K. We're multiplying that in INQ, and we're going to view that in the frequency domain.
So just as one thing here, we're no longer using that top signal source for anything relevant.
This one?
Yeah, so if you just... Yeah, let's just go with that, I guess.
Just delete it all. Oops, I'm going to need that throttle back, though.
If you just disable the add block and the Qt time sync, it'll... Oh, yeah. Sorry, I'm staring at the live stream again. I'm 10 seconds behind.
Yep,
yeah, you're good. Go with your route. It's fun existing in two time frames.
That's right.
Cool.
It has nothing to do with time zones either. All right, that looks ugly, but I think we understand what's going on. And I want to turn off the half. Where is it? Complex. Average. I don't get a choice of half on when it's a complex input?
No, you don't.
Yep, there we go.
And that's important, because we can't ignore the negative anymore.
Yeah.
So actually, can you please disable the half on the other? Well, yeah, let's disable the half on the other one. Let's look at equivalent plots here, because this is where things are going to get funky and fun. I think, anyways. So, okay, so confusingly here, we haven't labeled any of the plots.
I was just figuring that out. Let's fix that. Name. Floats.
Sure. Yeah.
And complex. Okay. Annoyingly, they are reversed from what they are underneath. That's okay.
We could fix that, but
I'm not worried about it right now.
Let's roll with this for a minute.
Yep. Okay.
So the fun thing that we have here is, so one, your data 0 is just 0. There's no signal there, so there's no frequency content, because it's both a constant value, so it's unchanging, it has no frequency, and it has an amplitude of 0, so it's not a DC offset. So there's no energy at 0 hertz. Cool. In the other component of our input, we have a real valued sine wave with a frequency of 1 kilohertz.
Mm-hmm.
And so it has a valid negative representation of negative 1000 as well. All cool. So here's the fun concept. Your input has two frequency components, positive 1000 and negative 1000. Our local oscillator, however, only has a frequency content of positive 10,000 hertz. Yeah. So if you doubled up the frequency sync that's complex and run your local oscillator into it, we would see that.
Wait, say that again? So this one here?
Yes.
Double it up. What do you mean by double it up?
Sorry, so take your frequency sync, your complex frequency sync.
Yep.
Give it 2 inputs.
Oh, I see what you're saying.
Yeah. So let's look at our local oscillator.
That's annoying.
Yeah. This is, again, curved lines were the lesser evil. So we see that our local oscillator has a positive 10 kilohertz energy content and does not have a negative representation. It is only a positive frequency.
Whereas our float input has is represented both positive and negative, because we okay.
So when we multiplied those, we did not end up with energy at negative 10 kilohertz plus minus 1K.
I want to try something.
Yeah. Just as a continued fun thing, if you did want to simplify these a bit, you could delete the float frequency sync, because you've already done float to complex, and you could run that into a third input of the complex one, whether or not you think that's useful.
So here's what I'm grappling with right now, is that the we've got a float source that we're converting to complex, with the other side of the complex being a constant of 0.
Mm-hmm.
How is that still positive and negative? What would we do here to make that just a positive?
We would take a copy and paste the float signal source, replace the constant source with it, and we'll do this as a 2-step process so that everyone believes us when we say we're doing this, and actually plumb that throttle into one of the two.
Yep, that's what I'm working on.
Cool.
So again, if you weren't here at the beginning, the throttle is just there to make this operate in real time. It's not actually changing the numbers at all. That's just a GNU Radio thing. Okay, so they're both sine.
Open the second signal source. So this is our quadrature component, and change the waveform to a constant.
Oh.
Because I want to do this as a 2-step process, and the amplitude to 0.
So that's basically replacing exactly what we just had.
Precisely.
Yeah,
we are going. We've just swapped. We're going to give ourselves more options in the future, but
looks exactly the same.
Looks exactly the same. We are only looking at the output here, remember? So let's close this. Open up the frequency sync and give it a third input, and grab the output of float to complex.
Okay. Yeah, this is going to be... If I were doing this for reals, I would make this less ugly.
So can you open up the frequency sync, and we will do something kind for the audience. If you go under config, we're going to label line 1 mixer, or mixer output or something. Yeah. Line 2 is local oscillator. And line 3 is input, or baseband.
Yeah. Perfect. Okay.
Cool. This will at least, the plot will be less ugly than
the graph, yeah.
Than the flow graph. Cool.
All right, so hang on, let me put this where... There we go. Now everybody can see it. So we've got our 3 signals. We've got our baseband is, again, a positive and negative frequency. We've got our local oscillator at 10 kilohertz. That's our RF. We're apparently doing VLF. We're talking to submarines here, apparently. And then our mixed output is the sum and differences. Okay?
Yeah.
Got it. And this looks exactly like what we had before when we were literally mixing in a constant.
Yes.
Yes.
So
okay.
Let's try and get rid of one of these sidebands.
One of these 2 sidebands?
We're going to get, well, both, but
okay.
Yes. We're going to get rid of one of the 2 of the green sidebands.
Okay.
And we'll see what the effect is on the blue signal.
Okay.
On the mixed output. So go into the signal, the constant signal source, change that to a cosine wave, and change the amplitude to 1. So equal to the other sine wave.
Equal to that. So basically, this is a sine, this is a cosine.
Yeah.
All right, so we're back to our thing. Anything else?
Nope, that's it.
What? Crazy talk.
Ah, ha, ha.
Okay, so explain to me what just happened.
You just canceled one of the valid solutions. So.
And it's freaking my brain out that it's a negative number, negative frequency here. But what that just means that we selected the lower sideband.
We selected the lower sideband.
So if
you actually start looking into, so actually I'm going to ask you to throw down a time sync with 2 channels and grab the output of the 2 signal sources.
Okay, so I swapped the sine and cosine, and now we've got upper sideband and a positive frequency there. That hurts my brain a little less. Okay.
So, well, but like, what did you just do, and what just happened, and how is that not absolutely blowing your mind? Right?
All right, show me the time sync. What am I doing with the time sync?
So, well, just pause for a second. And
okay.
You just swapped a cosine and a sine, and somehow you got a positive frequency out of this. And previously you were getting a negative.
Let's do that. Let's go back.
This is the thing. This is the wild moment where if you properly teach an undergrad this, or anyone else, this is where their mind, goes galaxy brain. And to be fair, I would love to figure out how to teach this really well, because this just makes me so happy and it's so cool.
Yeah. So okay.
So you have a negative frequency of 1 kilohertz represented as a sine wave and a cosine wave. And you then swap.
But I feel like representing that sine and cosine, the representation of that sine and cosine is just a representation of the phase shift of that 1 kilohertz signal. That's the part that I'm having a hard time with. Is that's a phase. By changing the sine and cosine, all I've done is I've changed the phase. How does that move the frequency?
So this is where the flow graph that I have comes in.
Okay.
And so, like, how much are we going to shatter OBS if I screen share, or should I walk you through setting this up? It's not particularly complicated.
Yeah, walk me through setting it up. Should I start up a new one?
Yeah, fire up another one, because we'll end up returning to this one.
Okay.
Because there are some useful bits, especially that time sync that.
Yeah, Nerd Garage is losing his mind because he's trying to explain to me what it is, and we'll get there. We'll get there. He's like, you're canceling out the phase, canceling out the relative phase. I'm like, okay, give me a second. All right, so what do I draw?
Okay, so let me jam mine onto the other screen so I can see yours. Okay, so I want you to throw down two. Actually, you can probably copy and paste this from the previous example. Copy the 2 signal sources, the throttle, and the float to complex. Yeah, copy, pasta. Cool. And I've got them the other way around, but this doesn't matter at all. And now grab a Qt GUI Constellation sync. Ooh, WX. Haven't seen that in a while. It's good stuff.
Yep.
So throw the output of the complex signal into that. And now open up the signal sources and change them to 0.5 hertz, because our eyeballs don't like things at 1,000 hertz.
Yeah.
And our brains even less.
You said you had them backwards. You want me to change this to cosine and sine?
I don't think it matters.
Okay.
It'll change exactly where the signal starts, but that's fine. So hit play.
Hit play. All right. Go away.
Save it as Constellation example. Or
I'm sure I misspelled that, but I don't care.
It doesn't matter.
Zoop, 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 zoop.
Okay.
I don't know if that's coming through on the stream, but it's going around in circles.
So we've got something cool here. No, don't page Ballant. He's busy at the moment. Okay, so we have a weird blob that's running around in a circle. And so, okay, let's build upon this, and when this will start becoming intuitive. So we'll close this, put down a time sync with 2 inputs, or just one. Actually, one.
Tangent for a second. I agree with Tim K on this one. How do I change the update period? I never understood how this works. Do I want this to be a smaller number or a bigger number? It's a period.
You want it to be a smaller number.
Okay.
It's 1 over the refresh rate.
Okay, so it is a
that
literal
should be
period.
100 hertz.
Yeah, okay. And it's still not doing it. It's not any faster.
Well, I mean, there's also only so much. Well, we're only going. Yeah, the blocks could be better. The display blocks could be better.
If only there were a newer version of this code.
I don't even think that helps. Nobody has paid attention. nobody likes working with GUIs. It's really sad. Every single summer, Google funds interns. Well, strictly speaking, they're not interns. They fund students to do development on open source projects. And every single year for the past like 8 years, we've had a improved Qt GUI project, and nobody's taken us up on it.
Yeah.
But yeah, so throw
All right.
down a time sync with one channel off the end of the float complex, and throw down a frequency sync.
Come on.
Because we're going to look at this in the time domain, the frequency domain, and a plot of what's happening on the complex plane, on the quadrature sampling plane.
Okay. No other changes?
Nope, just run that. And get yourself a good view here.
I don't know how to do that.
I don't know how you get a good view of this.
Yeah.
That's good enough. Cool.
Yeah, that'll do.
So first of all, our frequency sync is not actually going to be hugely useful, but let's, kind of
ignore all the noise down there you were talking about. That's like the aliasing and
it was well pointed out to me that quite a lot of that is actually going to be some of that will be the numerical noise that I was talking about, and the other bits of it will be the FFT window, or the Fourier transform window that's applied. You get side lobes when they don't actually exist. But
because we're the FF. Hang on. Wait a minute. Frequency sync. Let me make that a whole number of our sample rate.
At this sample rate, that won't matter.
That didn't do a damn thing. Never mind. Does it?
I don't know if you can even do. Yeah. Okay. Apparently. Yeah. Cool. Okay. It's just not applied.
Still no love.
It centered things a bit. I think here is where we're seeing numerical trash.
Okay. Anyway, what I was trying to do is I was trying to make our frequency and our sample rate and the FFT size all not relatively prime. What's the opposite? Like not have any phase delay from being off in numbers, and there's a term for this, and I don't remember what it is.
We're getting a bit dragged into the weeds here.
Yeah, we are. Okay.
Kit is correctly saying that if you disable the window, I think you'll get what you want. But
okay.
Wait, let's
Good
not
enough. Move on. That's not what we're trying to do here.
If you zoom in to the frequency right around that spike, I don't even know if we'll see it because our frequency is so low. Yeah, okay, so we can't tell, but trust us on this. It is currently representing, the one frequency that we saw correctly plotted. We'll put a much higher frequency in a second, and you'll see it go positive and negative. But
0.1 kilohertz. That's right, because our signal is half a hertz. That's what it is, because we're not looking at a 1 kilohertz signal. We're looking at a half hertz signal.
We are looking at a half hertz
signal. Got it. Okay.
So you can see in the top plot,
the
real and imaginary, the I and the Q components, so the in phase and the quadrature components of this signal. Chasing each other. And if you middle click on that display and bring up the control panel.
This is new. I've never seen this.
It's handy.
Yeah.
And zoom out or increase the X max a lot. Because this is a half hertz signal. Okay, so we've reached some limit here. That's sorry, the update rate's now horribly slow, but that's fine.
Got it. Okay. But you can see what looks like a normal quadrature signal.
Yeah. Yep. Because that's what we're putting in. We are putting in a quadrature signal with one frequency component. You are the worst peanut gallery ever. And so the cool thing, so here let's pay attention to one thing. Which does it look like the imaginary, the quadrature component, is leading or lagging the real signal?
In this case, it looks like the imaginary is lagging because the real signal is in front, so the imaginary is behind it.
Yeah.
Okay.
So it is negative 90 degrees from the real component.
Yes.
So now let's scroll down and try and dig into what on earth this rotating blob is. So there's actually, there's a great illustration that I should have dug up before this. We are looking at what happens if you take those, it's an XY sync, basically. If you had an oscilloscope in XY mode, this is what you would be seeing. So we have two sine waves going in, and we can see that the blob is rotating clockwise, because if you plot the real value, the in-phase value as the X, and the quadrature imaginary component as the Y, over time, that describes a circle.
And we're just doing it very slowly here because it's,
because we want to be able to actually
I want to be able to see it instead of just making it a circle, a literal circle.
So it is rotating clockwise. Close this, go back and swap the order of sine and cosine. And yeah, if you repeat your stunt there of zooming out, and if you set the trigger to auto, it may improve visibility.
Set the trigger to what?
Auto.
Yeah. Oh, sweet.
So is the imaginary now leading or lagging?
The imaginary is now leading. It is in front of the real.
By 90 degrees.
I will also point out that the schmutz down here looks like it has reversed.
It has, yeah. And we'll bump up the frequency in a second to see that a bit more obviously. And how has the direction of our rotating blob going?
It is going counterclockwise. It is going opposite.
Yeah. So we have now switched from we have negated the frequency. I can't remember which one is positive and which one's negative. There's one that's true, and we're going to figure that out experimentally here in just a second. But we have switched the sign of the frequency here by swapping the order of those.
Frank, yeah, I think so. Frank is asking whether all sources are magically synced, and I think the answer is yes.
They are. Let me take a moment and explain exactly why that is, because somebody here, including Frank, will find this interesting then. So if we close this top block, so what's happening here is the signal source blocks are producing values as fast as they can. Well, actually, sorry, let's be very accurate about this. So we can't close that. The constellation sync, the time sync, and the frequency sync started when you hit run on this program, all immediately try and display data. And it sits there and goes, well, gosh, I can't plot anything if I don't have any input data. GNU Radio scheduler, please give me data. And the scheduler goes, okay, you're all fed from the float to complex block. Float to complex, I'm going to call your work function, please give me samples. And the float to complex goes, well, gosh, no can do, sir. I need something at my inputs. And so it keeps traversing its way up the graph until something can actually generate data. So the throttle block, no can do, I need an input. That first signal source, though, says, oh, yeah, sure. How much do you want? And the scheduler says, I'm giving you an output buffer that will fit 10,000 samples. And it goes, and the signal source goes, well, yeah, okay, I have no dependencies. You want 10,000 samples? You got it. Fills those samples in. The float to complex goes, I really need that second input. The throttle block goes, I really need my input. The second signal source gets called. It does its work. also, let's say, on 10,000 samples, and boom, 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 it all flows down. So the trick here is that the float to complex block cannot operate until both of the signal sources have supplied at least one sample at its input. So that aligns them. And yes, Frank, this is why you only need one throttle block for the entire connected set of blocks. Because in the end, it'll be the weakest link. What am I trying to say?
The slowest link. Yeah.
Yeah. And so the throttle block, the way it works is, you know, the Constellation sync and stuff will try and consume data really fast.
That's why you don't have to put a sample rate in here anywhere. It just consumes as fast as it comes in.
Yes, true.
Yeah.
And it doesn't, the Constellation sync specifically has no meaning for the samples, because it's just plotting X, Y.
Oh, you're right. So the time sync does need a sample rate. Okay.
Because it needs to label the X-axis.
Oh, got it. Okay.
So it needs to be able to say what's the sample period.
Oh, so for the bandwidth. Okay, got it. So we're
and
not
the bandwidth. Yeah.
Yeah. Okay.
Sample rate also determines frequency. Tim is asking, why can't you have feed forward? Yes, this is exactly the problem. So if you had a block that relied on its own output as one of its inputs, GNU Radio Scheduler doesn't know what to do with that. There are ways of getting around that, where you supply your own initial values and stuff like that, but very advanced GNU Radio there.
You would have to put a delay line in the feedback or something. Oh, but even then, you still need to initialize it. Yeah. Okay.
The initial state problem is difficult, and you can handle it basically outside of GNU Radio's classical data handling. But it is possible to do. I've seen people do it. We want to make it easier, and there's a big scheduler rework project going on right now. And okay. I don't know that this is specifically one of the things being addressed, but it's certainly being talked about.
Okay.
But yanking ourselves backwards here a bit. Yeah. Let's start adding some knobs to this. So can you pull in a range widget?
Yep.
PS for the audience, this is also turning into a GNU Radio tutorial.
Don't care. I mean, I don't care in the negative way. I think this is rad.
Yeah. Right. So let's change the ID to be in phase frequency, or in phase _frec, or I_frec, whatever you want. But,
ifrec.
Cool. And the label, let's just go with just frequency for the moment, because we're going to play a bit of hot wiring here. Default value 0.5. Let's keep our half hertz basic. And let's go to the full theoretical range of these. So because these are real valued signals, real valued sources, they can't produce a negative frequency intentionally, like by convention, I guess. They produce a negative frequency at the same time as they produce a positive frequency. So you correctly set the start to 0, because conventionally we can't represent we don't say that it can do negatives.
Yeah.
We just take that as an assumed. The stop is half of the sample rate. Yes.
Yep.
Step size, let's go, yeah.
Or actually, not if I'm doing 0.5 as my default.
It won't matter, but yeah, okay. do half. Okay.
Counter and slider, yes. Okay. Okay. Cool.
Cool. So hit OK, and go into both of the signal sources and load I_frec in place of the frequency. Cool. And let's just fire this up.
And hopefully,
so we are going
exactly
to change
the same.
The frequency of both of the components in lockstep here. So we're not going to do anything funny with that. So you're now driving a What are we looking at here? What are we doing here? So, yeah, so what am I missing here? So yeah, so you're running. So let's not play with the band edges because
come on, this
aliasing
is
is
fun.
So if we look at just one signal here,
Okay. What frequency do you want me to set it at?
Just set it at 1,000. Let's go back to our 1 kilohertz. Why are we getting positive and negative here? What have I missed here? We have a sine, we have a cosine. What am I missing? Anybody in the audience know what I'm missing? Because I'm expecting there not to be a negative frequency, or I'm expecting there to be only a negative frequency. Tim's saying it's slipped samples. I would have guessed that myself, but that shouldn't be possible for it to slip samples. Maybe it's applying the frequencies separately. So let's hard code it. So if you go into the range widget, yeah, set it to 1,000 and just run that, just as a sanity check. So cool. Okay. So my
so
hypothesis
the issue there was that we were shifting the phase of our INQ that you shouldn't ever be able to do by changing the frequencies not at exactly the same time.
Yes,
okay.
These aren't. A second throttle wouldn't help here, Frank.
No.
The issue is that we aren't using locking, like in the programming sense, to set both of the frequencies at exactly the same moment. And so if one of the blocks is running as you're setting it, or runs in between setting the two, you'll get, a phase slip between them, which sucks. There's ways we could start going around this, but this will work for our purposes.
Yep.
So here we have a positive 1 kilohertz signal. And we can see that the imaginary is leading the real. So now through experimental experimental routes, we've figured out what the convention is. And it's probably not just convention. The math probably bears you out here if you work through all the stuff. So
I was told there would be no math. Okay. So
we won't do the math. We'll just trust that it works.
Yes. But okay, so we won't actually be able to slide that and get anything.
We can try it, and at some point it'll break. My guess is, so actually, what I would do is, if you want to make big changes, just type in the value so that we minimize the number of sets. As you dragged it, that would have been a lot of set calls.
Yeah.
And so it maximizes the chance that we'll get something. Interestingly, actually, as a bonus round for people here, you can see that we're now getting a positive and negative signal when we're only expecting there to be a positive. What we're actually seeing is a phase discrepancy between the I and Q. And so this is why you get IQ images and why some SDRs offer IQ calibration. If you don't have the electrical paths equal in length to your ADCs, or you have a sampling error between your ADC channels, this is what you get. So we've slipped the phase slightly between those two. And the result is that the FFT is giving us a little bit of a negative frequency. And while it looks really strong here, Mark, can you actually zoom in, like click and drag a box over the two peaks, just, only down to like -60 dB or something.
Over down to -60, like that?
Yeah, something around there. So we can see that one of them is at -8 dB, and the other one's at -28 dB, around it. So we have a 20 dB difference here. So it's a 1% power error.
Even though they look really similar, yeah.
Yeah. So the power of the negative frequency is 1% of the positive. So yeah, congrats, we've got an IQ imbalance.
All right, so, okay, actually, describing the IQ imbalance is, this might be the root of what I've been trying to get at, or what I've been trying to wrap my brain around.
Mm-hmm.
When you have your signal represented as a float, and you've got a 1 kilohertz tone in that float, the timing of when you hit your zero crossings and your peaks and your valleys and whatever else is what represents the phase. And when you take that same 1 kilohertz tone and try to represent it in an INQ, you can't adjust the phase of that 1 kilohertz signal in the, like, how do I represent this? I think what I want to do is I want to look at a 1000.5 hertz signal sampled at 32 kilohertz. Is that going to do what I think it's going to do? Is that where I'm going to see, like, where I'm going to see the INQ amplitudes going up and down as it shifts phase in the sample rate?
What do you want to see here? So a pure sine wave, a pure frequency component in the, we can run a pure sine wave into an IQ demod and look at what we get in the output. Sorry, so what do you want to get out of this? You want to get,
I want to understand, like, we've been talking a lot about the math of INQ and how to view them and all that. I'm still not grasping what a 1 kilohertz audio tone modulated up to 7.168 megahertz looks like on an INQ. Right? That's the part that I'm still trying to grasp. Is that
so when you broadcast out your radio, it's a float.
Yes.
It is a real valued signal because it's current / voltage on your antenna.
Yeah.
You don't have a complex number coming out of your rig.
Correct.
So actually, right at the beginning of this conversation, an hour and a half ago,
welcome to my live streams.
You described, I'm cool with it, and apparently the audience is too.
Yep.
So you described an ideal software-defined radio, something where you had an ADC jammed onto an antenna as your receiver, and you just sample fast enough that you can capture the entire band of interest. Conversely, on the transmit side, you have a DAC, you have a digital to analog converter, driving a voltage onto the antenna at a fast enough sample rate that you can represent your transmitted, the highest frequency component of your transmitted signal. And it's like, this is what the flex radios do for some of their bands. I don't know which ones are direct conversion, but this is literally what they do.
Yeah.
They have really fast ADC, they have really fast DAC. And if you're doing that, you can do it. I think you must do it purely in real value.
Why? You can convert from real to complex all you want. It's just math.
But you can't.
We were just talking about that earlier, Euler's function.
Yeah, so this is where I get super funky between converting between a complex number and a quadrature sampled signal.
I thought those were exactly the same.
Well, I mean, a complex number is just a point on this in phase and quadrature plane. All right, here's where I need to be very careful and start throwing in like, I have no ideas, because we're hitting this. We're hitting this point.
Okay.
What am I trying to say? If you are transmitting directly, you are not going through a local oscillator. It is sufficient, and you can transmit a single sideband signal with a real valued output.
Sure.
Because you are not doing any frequency conversions on that real valued signal. And so because you're outputting data fast enough, you can create a single sideband signal at 7 megahertz, and it's fine, because Shannon's theory and the sampling theorem says that as long as you're outputting more than 14 megasamples per second, twice the highest frequency of your signals component, then it's unambiguous. It's fine. And you can put an arbitrarily complicated signal in, and you get it out. And so single sideband doesn't have any issues here. We've just said there's energy here, there's energy here, and there's energy here.
Yeah.
If you are running out into a mixer, then it is beneficial, and I'm not going to say necessary, because this is where I'm going to get trapped, and hopefully somebody in the audience would know better, but it is beneficial or useful or possible to put a quadrature signal in and get what we saw, where we got a single sideband signal out, because we had presented the I and the Q that only gave the positive answer when mixed.
So yeah, you definitely don't need it. It's a design decision. You can either design your DAC and your mixer as a quadrature mixer, or you can design it as a standard heterodyne, right? Like, I mean, a standard single sideband radio, like my BitX 40, right? It takes a microphone and it mixes it with a local oscillator. You get the positive and negative images. You run it through a little tiny filter to filter out one of the two sidebands, and then you shift that up to the frequency you care about, amplify it, and transmit it, right? There's no I and Q there.
But what frequency is it doing the filtering at? And I think this may be the interesting
The first
point.
IF.
The first IF, yes, okay. So you, at the first IF, do get a double sideband signal.
Yes.
And then you filter one of them out.
Correct.
You mix it again with a real valued local oscillator.
Yes.
And you will still get two frequency components, but one of them will be outside of your bandpass filter.
Correct.
So it gets thrown away.
Correct.
So you have wasted power here. You've wasted power twice.
At the IF, yes. You've wasted...
At low power.
Yeah.
But you've wasted power.
Yeah.
Whereas if you used a quadrature DAC and a quadrature mixer...
Sure.
You wouldn't be wasting power twice. And you would not have to have these filters at the IF, which are fairly narrow filters.
Yeah. And hard to build. A pain in the butt.
Yeah.
Yeah.
So by using quadrature sampling, we avoid all those filters, because we are just directly producing the right value because we've done math on it.
Yeah.
I think that's the point. And here's where I'd love, peanut gallery audience and like future YouTube, like find me on Twitter, please. Like, is this correct? Like, is this why people use it? I know that when you get into digital communications and QAM and OFDM, like, complex numbers and quadrature sampling becomes a really native and natural mathematical expression of it, and that's where I'm more familiar with it.
Yeah, me too.
But like, for stuff like this, I think that's where the compelling bit comes in, is that you can simplify the hardware design a lot by not needing these filters, and so your single sideband ham rig still just works.
Yeah. Like if we were trying to do BPSK or QPSK on this would make a hell of a lot more sense, right? Your Constellation graph down here, you get 4 little boxes of signal, and you've got a literal sum of two sine waves that are 90 degrees out of phase, and you just transition from one amplitude to another on those sine waves, and your dot moves around that constellation graph. I get that instinctively. I understand the BPSK and the QPSK, and even like QAM64. You just have more amplitudes than just positive and negative, and you're able to look at it on that INQ graph and decode that. I still haven't figured out how sideband works in that. Yeah.
So one of the cool things that I ran across in, I think it was Alan's second video, and maybe here's, depending on how much you, I guess, dare to go through, he probably won't copyright infringe us, but he's got a diagram, and it's the audio input, and this is how to generate single sideband. And there's basically two methods. You can use a phasing method, or you can use the Weaver method. Go and check out his video. And like, Mark, I guess you should insert a link at this point in the recorded video.
Oh yeah, it's actually already in the description. I've linked to both of those videos already.
Yeah. Head to, where are we at? We're at 13 minutes into episode 171, IQ Signals Part 2.
Oh, you're asking me to bring it up?
Well, for the future audience, here's where to jump in there.
Yeah.
13 minutes in, I mean, watch the whole damn thing, but 13 minutes in is where I'm looking at. There's a plot that shows the real valued audio input, and then a crazy box called 90 degrees phase shift network. Somehow, you have to phase shift the entire range of audio frequencies by 90 degrees for each frequency.
Yeah, which is why that's a pain in the ass to do. You can do it with a very narrow band signal, with like the QCX. Actually, I've been looking at. It's a very narrow band audio receiver, and so he's able to do a 90 degrees phase shift on that very narrow band of frequencies, and it actually works out reasonably well. Trying to do it on 300 to 3000 is a lot more complex.
Yeah, and so this is interesting. So I'm just scrubbing through the rest of the diagram. I don't think he has this plot. The other method of generating single sideband audio is a method called the Weaver method.
Which is actually what I've got up on the screen right now. If you switch back over to...
Gotcha.
So I made I'm trying to do a dual single sideband receiver. So the goal of this project that I already had up was, I've got my RTL over here. I'm using a frequency translating fur filter, which is bloody magic, by the way. There's an entire wiki page on the GNU Radio wiki that describes all the things that a frequency translating fur filter does. Basically, I've got my RTL is centered at 7.1 megahertz, and it is sampling 240 kilohertz, which means it from 7.1 it goes up by half of that, so to 120,000, and down by 120,000. So the idea being that this was a convenient sample rate to grab most of the 40 meter band, right? And so it's 6.98 up to 7.24, 6.96 to 7.24.
2.2.
You're right, 2.2 and 6.98 to 7.22. Yes, so it's got all of the frequencies in that range, and it samples that and then makes that into a complex signal. The frequency translating fur filter, it will allow you to basically say, give me this little sliver of frequency, translate it down to around 0, because a complex number always represents 0 to some positive value and 0 to some negative value. So it's basically plus and minus half your sample rate. And then decimate it down to a smaller sample rate, right? So let's say, I've got 240 kilohertz of spectrum from the RTL, and I'm only interested in 3 kilohertz. right? So I'm going to take that arbitrary 3 kilohertz from anywhere in this 240 kilohertz range. I'm going to center it to 0, and then I'm going to decimate my sample rate down to, since I'm interested in 3 kilohertz, 6 kilohertz. Or actually, I think I have it at, the audio sample rate is 8 kilohertz here. So I'm actually interested in a 4 kilohertz band of spectrum, which means an 8 kilohertz sample rate. Sort of. Anyway, but it grabs that and it centers it and then it decimates down to that. So the output of the frequency translating FIR filter is a lower sample rate than the input. So you don't have all of the other frequencies on either side. And the magic in this that I still don't understand how it does it is it grabs frequencies from over here, shifts them into the 0 range, and then decimates, filters out everything else, and then decimates it down to a lower sampling rate. So freaking magic.
Okay, so sorry if I can jump in. Okay, so there's no magic here.
It's totally magic.
It's not magic.
Sufficiently advanced technology, man.
So, and maybe this is a cool place where we'll kind of cover core concepts again in a different way and see if it snaps for more people, including you. So we're going to go through basically two operations here. One, we are going to do a frequency shift. And so in your frequency translating block, that's the first half of the name.
Yep.
You want to recenter your spectrum to the area that is at negative 24.35 kilohertz. And that is a relative frequency from your initial carrier of 7.1 megahertz, or your initial center frequency.
Yes.
Your initial local oscillator frequency. There we go.
Yeah.
Assuming this were a single stage heterodyne, direct conversion, basically. Sorry, that's totally different things. I'm going to shut my mouth now. Anyways, it is relative to that 7.1 megahertz. So we're going to shift basically up. We're going to grab that. It's basically like you were grabbing, the x-axis at negative 24 and dragging it to 0.
Over to 0, yeah.
And we have seen that work with just a multiplication by a synthesized local oscillator.
So is it literally just generating a minus 24.35 kilohertz LO and mixing them?
Fundamentally, yes.
Okay.
It's doing it in a computationally efficient way.
Okay.
But yes.
Okay.
That is what it's doing.
And then the FIR filter is what ends up filtering out your out of band. You specify a bandwidth that you're interested in.
So you want a limited bandwidth around this new center frequency. And so we want to decimate by a factor of 30. But if we only if we basically kept one sample, threw away 29 samples, which, by the way, if you're following along at home and you want to have fun with this, there's the keep one in n block that you can use to do this. You could have it keep one in 30 samples, and that would be a decimation of 30. But the problem is you might have energy outside of this new passband.
That you'll undersample.
And if you just undersample it, it'll fold all of that energy into your new baseband.
Yeah.
And you don't want that. So we do a frequency translation, and then we do a band pass filter around our new center frequency. And the cool thing is you can do this as a low pass on the I and Q channels. Maybe that's an implementation detail, but that's cool.
Yeah.
And so you filter it, and then you decimate it, and you literally do the keep one in n, or you do something slightly more fancy, but
yeah.
So
the can you do both the translation and the filtering in the FIR, or is that are those two separate steps?
I'm not sure.
Okay.
I think of them as separate steps, but I have learned to not underappreciate FIR filters.
The FIRs are amazingly effective and capable. So a FIR filter is for those who don't know, a finite impulse response is what it stands for. Don't ask me what that means. I understood it at one point. But basically, it is a buffer. It's got a buffer of a certain length, and there are constants with each entry in that buffer. You feed values in this way, and it's kind of a shift register. That's a better term for it. It's a shift register with these constants on each one. I think it's literally just multiplies the constant by the value in each of the positions of the shift register, and then you sum the output of all of those values, and that's your output value. And then you input another sample, it shifts everything down by 1, it does the multiplication again, you sum all of that, that's your output, and you just keep going like this. What the hell is this crazy block doing? Math, amazingness. If you choose those constants correctly, you can get this shift register multiply sum output thing to do so many rad things. A simple example, like what we're using it here for, is as a low pass filter, or you could use it as a band pass filter, or you could use it as a high pass filter or a notch filter. You know, all these different things that you can accomplish just by multiplying these constants by the values in this shift register, summing the values of the shift register together, and outputting that. By intelligently picking what those constants are, you can do some magic stuff. And so that's what a fur filter is. Just that mechanism of multiply these constants, sum, and that's your output. That's what a fur filter is. And then the magic comes in selecting those constants. Do not ask me how to select those constants. Thankfully, for GNU Radio, they have this really cool helper function called furdes. So fur filter description?
Designer.
Designer, there we go. And then you can say, design me a bandpass filter using complex numbers, because the input, this is a complex fur filter here. And then you give it the parameters here. I think this is an amplitude. What is the sample rate? What do you want your low pass to be? What do you want your high pass to be? And how steep of a shoulder do you want on it? So in my case, 100 hertz. You know, so it tries to go anyway. However it decides that. You define it how sharp you want that that filter to be. The sharper the filter is, the longer the buffer is, and the more constants it has to do, and the more math it has to do. If you're willing to be a little bit looser on those slopes, it can end up being a much shorter buffer. So you don't have to figure out what those constants are. There are helper functions that do it for you, but fur filters are freaking magic. They're wonderful.
Yeah.
And they're super efficient. If you are working ever with a microcontroller that talks about having DSP functions in hardware, one of the common DSP functions is a multiply and accumulate, where it does the multiplication and an addition. So you multiply two numbers and then take the result of that and add it to a third register, right? And so this is a function that makes fur filters super efficient, because you just have to do however many single instructions as you have buckets in your fur filter, instead of having to do a multiply and then a move and then an addition and stuff like that. So it's just like some of those DSP functions are the kinds of things that you don't do a whole lot very often when doing normal computations, normal computing kind of math, but when you're doing these kinds of signal processing, it's the kind of thing that you do a lot. Similarly, like the SSE functions, what are the super advanced parallel math the vector math functions that the Intel processor has? I can't remember what those are, what they're called, but like the SSE functions, you might have a 64-bit word, but that 64-bit is actually 4 16-bit numbers. And I want to take these 4 16-bit numbers and multiply them by this other 64-bit representation of 4 16-bit numbers and perform all 4 of those multiplications at the same time. So I'm now using a single instruction cycle to operate on 8 different values, 4 different multiplications. And so again, it's a way of optimizing these kinds of things when you've got a whole lot of multiplications that you need to do, and each one of those multiplications is independent. This value times this value, this times this times this times this. You don't need to do those sequentially. And so being able to do all of those in parallel in a single instruction really optimizes things. That's all because of fur filters and that kind of thing.
Yeah.
So anyway. Tangent.
GNU Radio makes extensive use of this. We have a project called Wolke, which is the vector library of optimized kernels, and it contains these SIMD, single instruction, multiple decode implementations for all of these sorts of math operations. And so another hot tip, if you're using GNU Radio on your system, one of the things that isn't run automatically is a command called Wolke_profile. And you run that on the command line. It's no arguments or anything. You just run it once. And it will search through all of these possible SIMD instructions and benchmark them on your computer. And then it'll save a record of which is the fastest. And GNU Radio will use that automatically in the future. And so if we actually take a look at some of these, we can see there's a generic for like the Wolke 16U byte swap puppet, the very top, or second to top one. That had a fair number of implementations. And so we can see the top one, ran in like 260 milliseconds. The SSE2 unaligned goes 141. The aligned in SSE2 does 157. And then we get into AVX, the advanced vector extensions 2, and those go even faster. So we can get a, what is that, 80 into 250, it's a 2.5 time, 3 time speed up.
Oh, okay. So I'm sorry. I was looking around for what you were talking about. But that block right there is what you're talking about?
Yeah. So this is a single operation. So we are doing byte swaps on 32-bit unsigned integers, I believe is the convention there.
So generic is trying to do it in normal.
Literally, we wrote a C++ function to do that, or a C function to just do that. No fanciness.
Got it. And so
the cool thing is that will run on any CPU,
including like a little microcontroller or whatever,
or the brand new Apple laptop that
the M1
nobody knows anything about.
Yeah. Sweet.
Whereas then you have these hand-tuned ones that only support some other architectures. And so one thing that you're not seeing here is, for instance, any of the neon instructions, and those are the ones that run on ARMs. So we have ARM instructions, and there's people looking at adding RISC-V, and there'll be people adding, I just saw an article today, adding the new SIMD instructions for the Matrix coprocessor that's in the new Mac laptops.
Okay.
And maybe Stephen in chat would like to work on that.
That's right. I think Stephen, he says, I know something about that brand new Apple laptop as I'm on one right now. I think you just volunteered to help write some code there, Stephen.
Yeah. And AVX does come in multiple flavors.
What's that you hear? That's the sound of Stephen taking step backwards really quickly.
Oh, look, we're at 17 viewers now. I thought we were at 18 just a second ago. Okay. Back to the Weaver method.
Yes.
So your CPU is currently busy on one thread.
Yeah, you think?
Hey, I'm sure you've got others.
I've got 4. Yeah, well, between Zoom and OBS and everything else, yeah.
So apparently we do actually have a volunteer. General shout out. We have a great chat system at chat.gnuradio.org. Come and join. We've got a ham radio channel. We've got general chat channels. It's good fun. We're on IRC as well, if you roll that way. Hash GNU Radio on the Freenode IRC channel. To contribute to Wolke, check out github.com/GNU Radio/Wolke, VOLK. That's my pitch.
I'm going to let this keep running.
You should. It'll speed up all your GNU Radio stuff in the future, including GQRX.
Okay, sweet. Well,
anything that uses GNU Radio.
So I got a lot of stuff going on here. So we got to the the frequency translating fur filter, but we didn't actually go any past it. What I'm trying to build here is multiple SSB receivers. So I've got one RTL, and I want to be able to get multiple audio paths, audio outputs from that RTL, and there may be a much more efficient way of doing this, I don't know, but I'm trying to get multiple audio paths out. Like I want to have the FT8 bandpass and the Whisper bandpass and maybe the Morse code bandpass, and take those signals and feed them into the individual programs to decode them. For example, WSJTX configured for FT8, so that I can be sitting there receiving FT8 all the time from a RTL dongle and just use it for spotting, right? I want to be able to spot people who are calling CQ on FT8. Similarly, for Whisper, I want to be able to receive the Whisper signals that come in. And I want to be able to do it from the same RTL SDR dongle and have all of these automated things going on. And maybe add a third one here that will receive the CW portion so that I can run that into a CW spotting program. What's it called? Reverse beacon network. That's the word I was looking for. And so what I've built is these Weaver sideband receivers. So let me actually disable one of them. Just so, nope, not you. There we go. Yeah, that's going to break stuff. That's fine. And so, frequency translating for a filter. So what that's doing, let's step back to the beginning. We talked way long ago about the hardware and how much the hardware is doing, right? An RTL looks an awful lot like an antenna directly connected to a DAC, but it's not. It actually has a tuner in it. And so what we're configuring here is that I've got the tuner, I've got a dial frequency, where is it? Oh, no, nope, cancel. RTL frequency, there it is, RTL frequency. So I have set the tuner of the RTL to 7.1 megahertz here, right? And so what that's done is that is mixed the incoming signal with a 7.1 megahertz signal and brought that like plus and minus from 7.1 down into baseband, right? So we've already had our VFO and our first mixer and our first IF filter, right? So before it even comes out of the RTL SDL block, we have already done those first components, right? So I've got the 7.1, we've got a pretty wide filter of 240 kilohertz, but it's all down at baseband, right? So the output of my RTL SDR signal, this complex signal right here, is baseband 240 kilohertz wide, plus 120 minus 120. So like when we were talking about how, where in the heterodyne path, like you picture a super heterodyne receiver, where in that path do you convert it to numbers? The RTL is already doing that first LO, that first mixer, and that first filter, and our first IF is where we are sampling, right? So the output of this is our first IF. Now I'm taking it to this frequency translating fur filter, and that's my second IF stage, basically. So I am doing another local oscillator, which is effectively the FT8 center frequency. So what I'm doing is I have another variable up here. Where is it? Whisper FT8 dial. Oh, yes. So I tried to make all of this very parameter. What's the word that ends in ick with parameter in it? Parametric. There we go. So, like, what's the dial frequency for FT8? Well, it's 7.074, right? But that's not actually where we want to listen. What is our audio passband? Well, we want to start at 300 on the low side, and the high side is at 3000. So the audio bandwidth is 2.7 kilohertz. So the center of the audio, because again, we're dealing with complex numbers which have positive and negative audio, right? So we always want to know what the center of our passband is. So all of this is just there to calculate what the center of the passband is. So the audio bandwidth is literally the high frequency minus the low frequency. So you can do math in these variable blocks. So there we're calculating the bandwidth. Here we're calculating the center frequency, which is 1.65, which I think is, the high minus low. Oh, I could put bandwidth there. Anyway, divided by 2. What's half the bandwidth plus the low frequency, right? So anyway, you can figure that out. So there's our center frequency for the audio passband that we're trying to do. Then FT8 center frequency. Where the hell is this one coming from? This is a little bit of big math. So the FT8 dial frequency, which is 7.074 megahertz, minus the RTL frequency, which is 7.1, right? So that's how we get into our first IF. And then we are adding the FT8 center frequency. And then whether it's USB or upper sideband or lower sideband. So this is defined as 1 for upper sideband and -1 for lower sideband. So whether the audio center is above our carrier, the dial frequency, or below the dial frequency. Because remember, the dial frequency is the carrier that's not there for your sideband. Anyway, what I was trying to do is make all of this parametric. So all you have to do is adjust your dial frequency, like what frequency does your radio dial normally show, and then what is your audio passband, and then it figures everything else out. What that does is that results in the center frequency for the translating FIR filter, and so that is now bringing the output of this translating FIR filter is just the audio passband that for the frequency, the range that I care about, around 0. Plus and minus, so centered around 0. Just the audio passband that I'm interested in. So if you were to go to your radio and dial in this frequency and set your audio filters to that, a 2.7 kilohertz audio filter, IF filter here, what the output of that would be is what's coming out here. All right? So this is our second IF stage, basically. The output of this is, again, complex numbers. Now, this is the part here that I am accepting on faith a little bit, but is kind of the part that we're trying to explain here, right? So the output of this is already a complex number. So it is an IQ signal. We've already got our quadrature. We've already got our IQ of the audio. So in the context of the of Alan's presentation, he was talking about shift your audio by 90 degrees phase, right? How do you shift your phase by 90 degrees? Well, that's kind of handled already in this complex flow because we've already quadrature sampled. All of this started as quadrature sample. And so we're splitting out that complex signal into its I and its Q. That's what the complex to float is doing. That's taking our incoming two-dimensional number and splitting it out into its 2 different dimensions. Now, was it the Taylor mixer where you're mixing it with the center frequency of the audio passband that you're trying to get? Was that Taylor? Is that the one?
Sounds about right.
Weaver.
But this is a Weaver demodulator, yeah.
Weaver demodulator. Weaver is the name I was trying to go for. So we've got our sine signal here and our cosine. So there's our, our quadrature local oscillator. And the frequency of this is right smack dab in the middle of the audio passband that we're trying to get out. And go ahead.
No. Keep going, and then I'm gonna waffle because I don't fully understand this method, but a few things are slowly dawning in my head. So continue, and then we'll chat.
So we have 2 local oscillators here that are 90 degrees out of phase, and the chat room is, I think, correcting us on. Is it the Talo? Yeah, it's either the Talo or the Weaver. I think this is Weaver.
You've pulled it from the Weaver tutorial on the GNU Radio on the GNU Radio one, so I'm going to believe it's Taylor.
I think Weaver.
That's right.
Yep, I know. I'm having a hard time with this too.
It's 10:30 here, and
That's true.
Yeah.
It is pretty
Blame
late.
it on that.
Anyway, so we've got these quadrature signals that are generated smack dab in the middle of the audio passband. And then we feed those into our product mixers. Remember, a product mixer is literally a multiplication of the two signals. And if you look at the electronics of a product mixer in a conventional radio, in a hardware radio, it is multiplying the two signals together. Like if you represent the voltages of those two incoming signals as numbers, their amplitude, the output of it is the multiplication of those two values. Okay, so Nerd Garage is saying the Tayloe and the Weaver are different implementations of the same concept. I think ultimately the difference is where your local oscillator frequency ends up being. So again, we're mixing our sine and cosines in with the two different, the I and the Q coming from the complex to float, and then we just add those together, and that's your audio. Right, and then I have a null sync because reasons. Just kept my graph from breaking when I enabled and disabled certain things. And then we show it into a waterfall sync and then an audio sync here. The audio sync will go to at least my headphones. You may be able to hear it. So let's actually play this and see what happens. Can you hear that? And you don't have headphones on. You may not. The audio is incredibly low. Let me do that.
Add a multiply const.
Yeah, that's exactly what I'm doing.
We recently had an improvement to the audio sync, very recently, but it didn't bring volume control.
Yeah.
And I can understand an argument to be made that, volume control can really be done outside of GNU Radio for the most part. But it is also sometimes useful to be able to multiply by, do a DSP volume control just on the one sync.
Yeah, but mult. Mult isn't all that hard, right?
No.
That's not a whole lot louder, is it?
Do you have a test signal, or is this coming out of the RTL?
This is my actual RTL. So there's my RTL right there. By the way, my desk is a disaster. But it's an RTL plugged straight into my USB hub. I tried a little bit of choking on the interlink between it and a triplexer. This is a triplexer for 80, 40, and 30 meters. I don't know if you can read those numbers at all. It doesn't look like it's... Anyway, it's a triplexer, and so I've got it hooked up to an outside antenna, and I got the 40 meter going into my RTL. I have on the way another triplexer for 20, 15, and 10. My goal is to have a wideband RF and receive antenna come in. Oh, shoot. I think I broke my RTL. Whoops. There it goes. To have a wideband receive antenna come in and go to these two triplexers. The input to the triplexer has another output, like just in parallel with it, so you can cascade multiples of them. And so the idea being, have one wideband receiver come in, go to 3 different bands on one triplexer, another 3 bands on the other triplexer, take the outputs of these into their own RTLs and into GNU Radio to split out all of these bands and run a bunch of WSJTXs to receive all of this, like potentially on 6 bands concurrently, right? Spotting FT8, spotting Whisper, possibly spotting CQ, CW CQs, all like on one receive antenna. That's kind of what what I'm thinking of in my head.
Come see the polished version of this in March.
Yeah. Good luck with that. Yeah, well, I may not have all 6 bands, but my goal is to have at least 1 or 2 bands. Oh, that's right, because we're
Yeah.
Yeah. Oh, that's right. So Derek and I are presenting. Well, we've submitted to present. I don't know if we've been accepted yet for the.
Yeah, we have.
We have. Okay. QSO Today Expo. So we're going to be doing a presentation on this there. You guys get to see the work in progress. So here's the waterfall. You can clearly see the 15-second blocks of each of the different FT8 signals, right? I don't know if you can hear it very well if I shut up.
There's absolutely nothing coming to me.
Okay. Let me
But
turn that volume up a little bit.
I mean, that could be that I'm not getting it, like Skype isn't.
Oh, you know what? Skype is probably not going to get it. You're right.
Yeah. I can hear it on YouTube.
Okay. All right, so folks on YouTube should be able to get it. Anyway, so that is, they can hear it sounds like FT8. Yep. Guess what? It is FT8. So, all right, so let me go back to where we were before. 2 inputs, and I'm going to go ahead.
Just what are you trying to illustrate here?
Single sideband receiver.
Okay. Just walking through all the variations. Sure.
Yep. And actually, yeah, no, that's fine. So now I've got, I've demonstrated this receive chain with around the FT8 band. I've got another one going around the whisper band. So let's look at that. Now you should hear FT8 in one channel and whisper in the other channel. Now whisper is a lot quieter than FT8. But here's the input. No, my neighbors have whatever it is that's generating that hash turned on. So here's like the wide 240 kilohertz of audio, and you can see those hashes very evenly spaced. Here's RF noise. But you can also very clearly see here's the FT8 section right here. As you know, you see the 15-second pieces, and then whisper is somewhere, somewhere up here maybe. I don't remember exactly where whisper is, but we've taken this section, chopped it out, and it's just here, right? And we've done all of the receive and all of the demodulation and everything to turn it into a baseband audio. And then this is the whisper. Whisper is a much narrower signal. It's only 200 hertz wide. And so here's the whisper bandpass. I want to be able to take these two audio paths, whisper and feed it to an instance of WSJTX, and FT8 and feed it to an instance of WSJTX, and be able to receive all of these in real time continuously. Mostly left channel.
So badly need better waterfall syncs.
You know what? This gets the job done.
It does, which is why nobody seems to put a lot of time into it.
Yeah.
But it is fun to run these sorts of signals into the phosphor sync and stuff like that.
Yeah. So one thing I haven't thought about, and this is actually probably something that GNU Radio would be perfectly suited for, can I decode FT8 natively in GNU Radio? Can I decode whisper natively in GNU Radio?
Yes,
it's a topic for another stream. We're not getting into it now, but
this is something that I've badly wanted to see done, mostly for FT8, because I thought it would be a really great illustration, but whisper as well. It's certainly possible to do it. Nobody has done it to my knowledge, and at least for FT8, I'm not convinced that the entire spec is well published in a way that you could implement it straightforward. I think you'd have to do some digging around and some forensics basically to figure out some of the values.
Well, the spec is there. I think the spec is well understood.
The
magic.
I agree with that.
The magic that Frank Taylor does to pull it out of the noise, maybe not quite so much. But the actual encoding spec, I think, is pretty well understood. Yeah, who's going to read Fortran, Frank? Frank says, it's published in Fortran.
Yeah. No, that's exactly the point, it is published in Fortran.
Yeah.
And so I can probably read it in a deep pinch, but it's definitely not quick.
Yeah.
And I don't think that the written documents are completely sufficient to implement your own one standalone. I think it's close. It certainly get you very close,
Yeah.
but I think you'd have to dig around for some of the parameters and stuff.
Okay.
But for instance, I don't know if it's in the version you have, but FreeDV and Codec 2 are both included.
Yes. Yeah, I do have
Cool.
the audio encoders there.
Yeah.
Yep. Okay. So here's a pro tip. When you're getting started in GNU Radio, there's no search bar there. And I spent like the first several hours just poking around in here trying to figure out what the heck is going on. Click the little magnifying glass, get your search bar. Now things are a lot easier to find. Pro tip.
Fix that. Why don't you fix that?
So at the very least, I'm running an old version. So I'm not going to make any complaints about the software until I get on a current version and know whether the bug is still there or not.
It's still not there on the build from today.
Yeah.
But I bet I can fix it right now.
Just have that default to 1.
Yeah.
Or default to on, yeah. I mean, honestly,
GRC,
I don't know why you would ever want to remove it.
Block tree window. Search entry. Position. Update tree. Set enable search false. Line 86 of grc GUI block tree window.py. If you set it to true, it'll default to being visible.
You know how I got GNU Radio installed?
Do you want to do that?
Sudo apt install GNU Radio -companion. I have not built anything on my machine.
You don't have to. It's in Python. You want to do this?
Pete's sake. Okay, hold on. Where's my cursor? There it is. We're going to go hack some things. All right, so it looks like my Wolke completed, but I can't grab that because it's under the window, so we'll just do this. Where are we headed?
Okay, so your install will be either in /user local or /user. So can you type which GNU Radio or _companion? Yeah, or dash, yeah. Okay, so it's in /user. So we want to be in /user. It'll probably be, no, so we need to grab the, look in the Python one, which I think will be in lib Python something. Which
version is it going to use? 3.7?
Honestly, it's probably, no, it'll be the 2.6.
No. Seriously? You guys are still on 2?
No, we're not. You're just on an ancient version.
Oh, well, fair enough.
Python, GNU Radio 3.7 didn't have Python 3 support. GNU Radio 3.8 has Python 2 and Python 3 support. And nice.
Dist packages, there it is.
So you're looking for blocktreewindow.py.
Dist packages.
You can probably just search.
What was the? Give me the name again.
So you need to go into grc.
What's the file name?
Just cd grc GUI and open up block tree window. I hope the chat's enjoying this.
Real-time code. You said 87?
Well, I mean on my version.
Well, la-ti-da.
But it shouldn't be that different. Search for set _enable _search, or just search. Oh, there you go. It's yeah. This is, for the chat's benefit, this is a significantly older version of GNU Radio. the 3.7 to 3.8 jump was very significant. It took a while to get out, and it's been great. Oh no.
Curses.
Oh. Oh god, maybe that just shows the side view. Anyways,
Yeah, this is not what we need to be doing.
No, it isn't.
Hey, Nerd Garage, don't you be hating on Vim. This is my preferred editor for most things. Okay, Derek, I'm hitting the end of my limit. Not the least of which because I have to pee, and it's getting pretty late for you as well. So, what did we accomplish today? We looked at a lot of different signals. No, that's not the one I wanted. I wanted to open up some of the one. Go ahead.
I suppose one of the main things that I think was interesting is we worked our way through what is a complex signal, as a pair of sinusoids, that the sum of the sinusoids at the same frequency give you another sine wave. And this is a property unique to sine waves, basically, that depending on the phase relationship of the sine and cosine, or the I and the Q components more accurately, you either get a positive frequency or a negative frequency. The thing that we didn't really get to talking in detail about is that rotation that you're seeing, whether it's rotating in the positive direction or the negative direction, that you can think of that as each sample is an amplitude value that has been phase rotated, has had its phase adjusted slightly. And the rate at which the phase is changing gives you your frequency. So if you're adding 90 degrees every sample, then you have a frequency component that is your sample rate divided by 4. It'll rotate all the way around one cycle in 4 samples. Does that make sense?
Yes, but I don't.
I may have jumped back.
Yeah. I'll be honest with you, my teeth are floating right now, so my ability to be able to understand new information at this point is going to be limited. Yeah.
So if you're adding phase, phase every sample, then it'll be rotating in one direction. If you subtract phase every sample,
yes, that I get.
It'll rotate in the other direction. And this is the difference between a positive and a negative frequency. It's a negative rate of phase change or a positive rate of phase change. And you can't represent that with just a real signal. You need complex numbers to show negative phase change.
I mean, that just sounds like a lower frequency, though, right?
It's not what the rate is, it's whether the rate is positive or negative. So if you're adding 1 degree every sample, it'll take 360 samples to rotate once.
Yeah.
If you're adding 10, it'll take 36 samples to rotate. You have a 10 times higher frequency. If you're subtracting 10 degrees every sample, it's the same frequency, but negative.
Yeah, I'm still not wrapping my brain around. I still don't have an instinctual understanding of this. I still don't have an instinctual grasp on these details. So I think I'm going to need to play with this a little bit more.
Mm-hmm.
And I think I probably need to jump on, or finally get up to date and get a recent version of Ubuntu. See if I can. Yeah, Unity is dead, unfortunately. But I need to get a more recent version of GNU Radio. GNU Radio 3.8 does not have a build for 1604, for Ubuntu 1604. I went and looked for it because there are requirements that don't exist.
Mm-hmm.
So.
And in fun news, we just yesterday, or was it Friday, branched 3.9.
Okay.
So the release is around the corner.
Very cool. All right. I do need to get moving. Thank you, Derek.
Yep.
I appreciate the time. This was a lot of fun. I think I can understand the complex stuff enough to use it. I still don't fully grasp what those signals are looking like, but I understand enough how to use them. That, like, for example, I mean, I was able to build this, right? And to actually make a usable thing. With this, I was able to split out the different chunks and make it work. If we just look at it as this is the first stage, the output of this is my IF, here's the second IF mixer, the output of that is baseband, and then now I need to actually decode that baseband complex stuff, do a single sideband demodulation on that into an audio, a float audio signal, and then for that I can send it into my audio sync or view it in whatever way I want, right? I'm tempted to grab this and turn it into a single sideband demodulator module, right? Or maybe even include the frequency translating FIR filter into it and just turn all of this into a block. You told me on Twitter once how to do that, and I have to go back and take a look at that and then actually go build that block.
It is a hierarchical block. And so I don't know if this will work on yours, but if you select one of those demodulators from the complex float up to the add block, I would suggest leaving the FIR filter out.
Okay.
Because it's technically not a necessary part of the SSB.
Fair enough.
And
fair
you
enough.
right click on one of those blocks. More, create higher. And now we'll see if it does anything.
It doesn't appear to have.
I don't know whether you need... I don't do this very often, but anyways, this maybe this is a thing for another day. You can grab pad syncs and pad sources and stuff like that, and those become things. But yeah, we'll do it another day.
So Nerd Garage is asking if there's a Discord where we can find us, or just IRC. For me, the best place to find me online is Twitter. I am Smitty Halibut, SmittyHalibut. Derek hangs out on, I see you on Twitter, but you're also on the GNU Radio chat, right?
The GNU Radio chat is the #1 best way to find me for live conversations. I'm on it incessantly. The Twitter is the other main way I have people reach me for random stuff.
Yeah.
And that's just Twitter, Derek Kozel.
And if you're if you follow me on Twitter, I tweeted out a link to this video and mentioned him in it. So Kozel is Kozel. All right, Derek, thank you so much. Chat room, thank you so much for showing up. Tim K, Nerd Garage, Frank Werner Krippendorf. Did I get that right? Forgive me if I butchered that. Those are the ones that I see popping up a bunch. Bill Mungavin and Stephen Benke. And then earlier, I haven't seen Kenneth or Nick popping up and throwing peanuts at us or doing the whole Statler and Waldorf thing very much. And then IK04 is another person. So thank you all for joining us. And if there's anybody else in there that I missed, forgive me. Yeah, we're going to go ahead and end it here. Thank you, Derek. I don't think this will be our last one. I want to do more. I want to, well, at the very least, we're going to be talking about the this multiple receiver project for the QSO Today Ham Expo. So, yeah. Thank you very much, everyone, for coming by. We'll talk about something up next, 73. Lots of a lot of people are bringing up, now that I actually mention people's names, Martin Buring. Again, forgive me if I've butchered the name, but that looks... Okay, Martin looks like the only new name. Yeah, so Thank you, guys. I appreciate you watching us. I'm Smitty Halibut. You can get me on Twitter or YouTube here. I am an occasional host on the Ham Radio Workbench podcast, which is kind of where this conversation started. So thank you to George for introducing me to Derek and giving me the opportunity to go straight to one of the sources, not the source. He is very careful to pronounce. So like, I am not all of GNU Radio. But he didn't step backward fast enough when people said, all right, we need to find leaders for this thing. So is that about right?
It is a great way for me to support the project because, as we can tell, DSP I have some ability in, but not nearly as much as some of the other folks.
Perfect.
So I'm happy to help organize things.
Yep. All right, guys. Derek, you have anything you want to say or promote while you're here?
Just the same things I've said before. Please do join us, chat.gnuradio.org. There's tutorials and stuff on wiki.gnuradio.org. And catch me on Twitter at Derek Kozel. And this is Derek, MW0LNA. Great chatting with you, Mark.
All right. Great chatting with you. I am Mark, KR6ZY. Thank you so much for watching, and be good humans. We'll catch you next time. And then this is the weird part where I wait for you to wave in the live stream so that I can click stop. There you go. There you just waved. All right.